Good morning, Level 3 Physics. Welcome back to Familiar Places with Familiar Faces. That was close, wasn't it? And it makes you wonder just exactly what does the period of a pendulum depend on. We're going to have a go today at working out exactly what the period of the pendulum does depend on, and we're going to start by doing an analysis of the forces that act on it. So that's your pendulum there at the amplitude position, and the forces acting on it are going to be obviously gravity going down and the tension force on the string acting along the string. And you can see that we can define the different variables in this because we've got the arc that the pendulum follows is the displacement, y, and the length of the string, same in both places, is going to be l. And we know from our mathematics that we can work out the angle in radians from the arc length and the radius. And the other thing we know is that to work out the net force here, we need to split gravity into two components. One component that opposes the tension force on the string, so that the net force along the line of the string is zero, the pendulum's not moving that way, and then a force that acts perpendicular to the string along the arc back towards the equilibrium position, the restoring force. And once we've popped the angle in there, a little bit of trigonometry shows us that the size of that force, the restoring force, the one that we care about, must be mg sine theta. Okay, so the next step is to persuade you that sine theta and theta are just the same thing when the angle is small. So we're going to sketch up a sine theta graph. And you know it looks something like that. We're only interested in angles when theta is small, where theta is less than around about 10 degrees. We're interested in this region here. And in this region here we can see that the sine theta cuts through the origin at about a 45-degree angle, which tells us that when theta is small, sine theta is around about equal to theta in radians. And we're going to use that fact, and we're going to substitute it in over here, where we worked out an equation for our force. And then from our definition of the arc length and the radius, we know that theta is just y upon l. So those are force equations. And we know that F equals ma, so A is F over m. We're just going to divide out that m to write down an equation that looks like that. Acceleration is minus gy upon l. And that looks really familiar. That looks a lot like our standard equation for simple harmonic motion, which has the form A is minus omega y. And what we can see from comparing A is minus gy upon l and A is minus omega squared y is that omega squared must be g upon l. And so omega must be the square root of g upon l. And omega is 2 pi upon t. That's from our definition of what we mean by the angular frequency. We're going to flip both those fractions the other way up and rearrange it to make it t equals. So what we've done here is derived the equation that links the period of the pendulum to the factors that it depends on, which is the length of the pendulum and the acceleration of gravity. Turns out Nothing else matters. Size of swing doesn't matter. Mass of pendulum doesn't matter. Only the length and gravity, and that assumes that the size of our swing is small. If the size of our swing is great, sine theta is no longer equal to theta, and in fact we stop doing perfect simple harmonic motion because no longer is the restoring force proportional to the displacement. And so the skill that we've learned here is how to derive an equation for period given the force that acts on a body. So what I'm hoping that we're going to be able to do now for practice is that you guys should be able to work out what factors does the period of motion of a mass on a spring depend on.